Okay, I guess uh, okay, so today what I thought we should do oh okay. So actually maybe that was the reason why someone did in the chair. I thought we were discussing whether is there a purpose of your group that so um so I figure okay it would be useful to talk about two other types of rank. So you know we have spent a lot of time talking about the rank of a matrix or a rankable tensor, but there's also a different type of rank called the non-negative rank, which has a lot of applications. So that's also a useful one to discuss. And another one which is called the symmetric rank for that. So that way I feel like we have covered all the variations of the concept of rank. That's how that relates to tensors and tensor network. So for that, so yeah, like the rank that I'm going to tell you about today is called non-negative rank. Okay. I'll start today with matrices, and then next time we'll talk about more of the tensors and other things. So first, as you might imagine, okay, it is called non-negative rank. The idea is that this is going to be defined from matrices which are non-negative. So first, we have to talk a little bit about what we mean by a non-negative matrix. So this is going to be defined for non-negative matrices. Okay. So there are actually three useful definitions of what a matrix with a negative is. First is like the more like the definition which is more like preferred for a mathematician. And that's kind of like what you probably look at before in different contexts that's called like positive semi-definite matrix. Okay, so one definition of what it means to say that a matrix is non-negative. So one possibility, let me write it like this. Is this idea of like a matrix being positive semi-definite. And what that means for matrix, the positive semi-definite, is that first it's a symmetric matrix. So this would only apply for, so here, this is for, so asymmetric. And once you know that asymmetric, it has eigenvalues, which are not real numbers, and then you just ask for all those eigenvalues to be non-negative. Okay, and you would ask for the eigenvalues to be non-negative. And that has a lot of useful character. I mean, there's different ways to characterize this, like being positive semi-definite. Um, so it's really like a very useful notion. For example, we have seen some of those already. If you had like a random matrix and you do A transpose A, you know, that is like maybe I should have called it, I'll call it N, for example, like example, like a classic example of these are if the matrix A is M transpose M, or A's and transpose for like an arbitrary rectangular matrix, that those would be positive semi-definite almost by default, you know, if you kind of like work it out. So these are uh positive semi-definite. Um and those are like the type of matrices that consider, like, you know, for this first problem, for the SVD decomposition, so you can kind of like see why they are useful matrices. These though are not the ones that I'm going to be interested in. for the next 2 or 3 classes, I'm going to be kind of like interested in the more kind of like naive definition, which is a matrix is not negative if all these entries are not negative. Okay, so it is like a more down to probably like the first definition, like someone who's taking linear algebra would have guessed, like this is kind of like very fancy definition. Like so, but that other one is more applicable to probability theory and other places, which I'm going to tell you about today. So the one that we'll do today, so another possibility, another option would be to say is that a matrix A is non-negative a non-negative matrix if all its entries are non-negative. Okay. This is not as elegant as the other one in particular because that is really specific to the matrix because if you change the basis, or you do like a change the basis then that messes up the non-negativity, right? That's specific to the representation of the matrix. It's not something about the linear transformation. You can think of a matrix representing a linear transformation. This is a property of the linear transformation, but doing a non-negative matrix in this other sense is really specifically that the actual representation of the matrix you're choosing. So this really is not, this is kind of like specific to the matrix and not the linear transformation it represents. Okay. I'll give you like a few examples, which I'll kind of like develop more like next week. There's this thing called like latent semantic analysis. I don't know if you've heard of that, right? But here's but I'm mentioning this one because I will say more about that next week. So let's say that you have some documents, and I'll think of the documents as a collection of words. Okay, so I'll think of some. So here I'll think of documents. So the input is kind of like some documents. You think as a collection of words. Okay, so the document, just to have like something very down to earth that you could write. I'll just write 3 documents, okay? So document 1, it will be cats like milk. Document 2 will be dogs like bones. Okay, they're very basic. They're very basic. The kid is just learning English, right? So they're just like learning how to write. And then cats and dogs play. It's kind of cute. So cats and dogs play. But like literally, like this actually practically you can imagine that the documents could be like actual books, like Shakespeare novel, or like just like a document like for a lawyer, like for a trial, like it really there's no restriction whatsoever in what it would mean, And so here, how many? Okay, so we have 3 documents, and how many words? Distinct words we have. We have. So the words. Okay, my words are cats, like, and then milk, dogs, bones, and play. So hopefully that's correct. So there should be 7 words and 3 documents. Okay, so one way to kind of like try to apply some linear algebra technology to something like this is that you represent this by a matrix. Okay, I think this is called like sometimes the work by document matrix. So what was the name? Term by document matrix. Okay, so you construct a matrix called the term by document matrix. Okay, and basically, the entry of the matrix will just be like the frequency or probability on which like a particular word appears in a given document. So just to kind of like show you how that looks like in this case. So I have 7 words and 3 documents, and so it's going to be a 7 by 3 matrix. So think of this document column as the columns being referring to document 1, document 2, document 3. And then of course we just choose like an ordering for the words. I mean, obviously all of this is up to how do you decide to order things. Like milk, dogs, bones, and flame. Oh, and then okay, so like for example, so what is the entry corresponding to cats in document 1? You just count how many times cats appear in the document or the sentence. In this case, it just appear once. But you will normalize it. So I'll write it as a probability as 1/3 because there are only 3 words here. So it's kind of like a frequency, how many, if cat had appeared, if there had been like 5 words and cat had appears twice, it's 2/5, right? So it's just like a frequency of how many times a word appears in the particular document. So for cats, let me write them in the fractions in the other notation because otherwise they won't fit. They won't fit well. So for the first document, cats like milk. Those are the first 3 rows. It's 1/3, 1/3, 1/3. There's a bunch of zeros everywhere else. And then you kind of go like that with the other, right? And so like appears. Cats does not appear. Milk does not appear. Dogs does appear. Bones does appear here. 0, 0. And the other one is the same, but because it's 4 words, it's going to be normalized by 1/4. I think it's 4 in the denominator, right? So half 1/4. Then there's no like, there's no milk, there's dogs, right? And no bones, right? And appears once and play appears once. Okay, so you see, like this is kind of like what the matrix is represented by in this case. And the way, if you do it this way, it's kind of like easy to see that every individual column, the entries add up to 1, right? You add up the entries along each column. So in this matrix column wise, you get 1. So this is sometimes what's called like a column stochastic matrix because the column wise they add up to 1. Okay, so this is a column stochastic matrix. So this is like a clear example of a negative matrix now. So you a little bit of what you could do with it in a moment. And then And we have other examples of like, non-negative matrices with this. Like for example, a joint probability distribution, right? If you have two random variables, we had when we talked about the joint probability distribution. Another example was if you had two random variables, or two experiments. I think I called them experiments. I don't know if I use a magic word random variable, but if you have two experiments, X and Y, two experiments, right? If M, like X takes M possible outcomes, right? And Y takes N possible outcomes, right? Like the joint probability, right? Like the joint probability matrix. It's kind of like, as you can remember, it was like this matrix Pij, where Pij is the probability that like outcome I from X and outcome J from Y, like get measured, right? However you want to think about it. But in this case, because we represent the joint probability matrix, it's not that each column or each row separately has to one, but all combined, right? In this case, all combined add up to one. And and then there's this other example, which are like the row stochastic matrices, right, where the rows add up to one, but that's just like the transpose of the column stochastic matrix. So genuinely, and I'll be more precise about this. Like really, the only two interesting examples of the negative matrices are either column stochastic, or like the kind of like the joint distribution. Like, either the columns add up to one, or all the entries add up to one. Because you can always do like a normalization type thing where you kind of like set it up as one of the two cases. But I'll put it probably like as an example problem or something like that, so that it's kind of show it, but it's not like an easy. So essentially, these column stochastic matrices and joint probability distributions covered after some normalizations, like basically scalings. These cover all the possibilities of what a non-negative matrix would be. So just as a remark, and again, I'll be more precise later about this. After normalizing, column stochastic matrices and joint probability distributions are the only interesting examples. And taking transpose. After normalizing and taking transposes, because like you may need to transpose to turn a row stochastic one into a column stochastic one. Oh, what happened here? Column stochastic and matrices and joint probability distributions are the only interesting examples.
Since we know in the language example, right? Like if you probably also make like a monotone chain of matrix with this example. You take the previous word and have the next word. If you have one more, I guess, token, which is like beginning sentence and end of sentence.
Oh, so
And you can square matrix, which is
I think, there's some variation. I was going to mention one later, that kind of like, involves kind of like setting it up as a tensor. Because here, I haven't said this in a moment, right now, but in the case of the documents, right? This is sometimes what's called like a bag of words representation, because you're just counting the occurrences of the words in the document. So you don't care in which order the words appear, right? Which one is first, which one is last. So, which is obviously won't capture fully like an actual sentence, right? Where like the order does matter. So you can, I think one approach is kind of like to add an extra uh, or leg, like kind of like do like a sentence where you kind of like put them in sequences, kind of like more like sequentially. Um, and maybe you could do it the way you're saying as well, kind of like to just, yeah, if you think of the chain, like kind of like which is the first one, which is the second one, and so on. But yeah, there are like fixes around it, but kind of like the more basic, simple example is kind of like in this model where you don't care about the order, you don't care about all of those things. But yeah, then they're kind of like more like careful like refinements of it. But there's one on with the tensor, which obviously I'm interested in showing you about later, so that you see how this generalizes the tensor, right? But they're like, I think it's more like you do have to kind of like think of the words being uttered in a temporal way, kind of like in an order that's probably more related to what the Markov chain thing that you are saying, if that makes sense. Yeah, I think that's basically like what their direction corresponds to. Yeah, like that's not about right. But but I'll show you like probably, but I think next week before the break, we should be able to get it done. I just felt like saying, okay, here's an actual example of like a non-stochastic matrix. I will show you actually how this is related to this non-negative rank that I want to define in a moment. Um, but yeah, no, there are definitely more complicated variations. Although this is like this latent semantic analysis is pretty popular. Like, it's sometimes actually useful when you kind of like are searching like for a document that's about law or about economics. This is kind of like one of the more basic approaches to kind of like sort them out into topics. I'm going to show you how this is related to topics, like how do you extract the topics from the data. That's related to the non-negative, right? You'll see that in a moment. Uh, okay, so but for now, I was just setting it up like, okay, non-negative matrices are kind of like, that's all my point, like with these two examples. Um, Now let's think about what was the rank of a matrix, just back to beginnings, right? Back to the start. Okay, if you had a matrix A, right? If A was an M by N matrix, okay, like there are like two ways for our class that we're thinking about the rank, right? So the rank of A, which I'll just call R. Well, let's call it, well, yeah, let's just call it R. So that was right, like two ways to think about it. That was the minimum integer, right? Integer that allows you to express for which A is a sum of the rank one tensors, right? For which A is a sum from what I equals 1 to R of the rank one tensors. And the other one, which is kind of like more like from the, I guess this is all related ultimately to the FTP. But you can, if you rearrange the U's and the V's as a matrices, right? You can express this as a product to make this as U and V, right? Or UV transpose, I suppose. Or it's just the same, which also means that you can find matrices U and V, right? You can find matrices U and V for which, well, I'll just use kind of like the notation, which is kind of like more similar, like from the infinity decomposition. as product of movie transpose. And then again, just for the numbers to come out nicely, you know, if this is M by N, then you had to be M by R, and the transpose would have to be R by N, right? So that it all ties up.
Yeah. So far we're assuming R is between 0 and.
Well, remember the rank, like, I mean, you can prove like, I mean, you can actually show that the rank is always less than M or N, right? Like, and that's actually not too bad to show, you know, so, but yeah, no, like, it would always be between, like, it would never exceed the number of rows with the number of columns of the matrix, right? So, yeah, I mean, you don't have to put, I mean, if you just start with this definition, you know, yeah, you can definitely show from this definition. Because you just like write down, you just have to kind of like break the matrix into like a sum of like a column with a bunch of zeros plus another, but you know, like you just kind of like do it one column at a time. Just keep like one column at a time and just fill the rest with zeros. And that is you should be able to reconstruct that as a tensor product, you know, between like the columns and like one of these basic vectors or something like that. So it can be, on the other side, I'm trying to say that definitely you can prove that it would always be less than 10 or 10, like directly, almost like without much problem. And okay, but now you see where maybe where I'm headed with, oh, I now want to define a non-negative rank. Oh, I'm just want to demand that in any of these competitions, all the entries are non-negative. So let's just do that. So the non-negative rank would be that you can rank the minimum R for which is a direct sum, the sum of rank one tensors where all the entries of the vectors are non-negative, or that you express that as a product of two matrices where all the entries, all the factors U and P are non-negative. It's just I'll use different letters for the matrices because just to teach convention so that you don't think that's related to SVD. But so what is the non-negative rank of a non-negative matrix? Okay, so I'll call it R plus. Okay, it didn't make sense. So R plus of A, right, is going to be the smallest integer, right? Smallest integer for which A, well, first I'll actually write it first as a matrix because I'm just using the conventions from this latent semantic analysis. It's kind of like annoying because everyone changes the letters for the matrices from one source to the other. So, you know, they usually write them as, I mean, it's one of the following, they write the factors as W times H. So here again, M was M by N, and this would be M by R, you know, R, and then this R by N. But the idea here is that W and H both have none, both the answers are non-negative, right? So only non-negative entries. Or equivalently, you just work it out. Like that is the same as saying that is a sum of rank one tensors, but like the factors of like these vectors all have non-negative entries. So this you can also write it this way. I'm just going to call them WI and HI just to follow the convention here. But so like the entries of WI of the vector WI and HI are not there. Okay. Uh, well, first I'll mention in a moment why this chemical definition, right? Concept, but at a minimum, it's some plausible that there is like some relationship between the regular rent and the non-negative rent, right? So there should be at least an inequality, right? So anyone wants to take a guess, like what could you say about the two? Yeah. Well, they won't be the same. That's not necessary. Like sometimes they will, but not always. I mean, it is a bigger ask. It is a bigger ask to ask for the composition to have all the entries not negative, right? Like, like if you think about what, like, if you just think about it from the tensor product perspective, right? Like here, the regular rank doesn't ask anything about the entries of the vectors, right? Whereas the non-negative rank does ask the entries of the vectors to be non-negative, right? Yeah.
Why do we care about the non-negative?
Oh, that's what well, I still haven't said that part, but yeah. But it's kind of like, well, um, right, it should be bounded by below but okay, so. Okay, so here's my claim. My claim should be that the regular rank of the matrix is greater or equal than, is less or equal than the non-negative rank. Let's see if that makes sense, because if you had, if you had a decomposition, as a sum of tensor products where all the entries are non-negative, that will also in particular give you like a decomposition like in the regular sense. And so that, how one is like, okay, so also you mark that it means like, like one is like containing one sort of tensor product decomposition is comparing to the other. So it is like, like, yeah, so. Because if you express A as in this way where all the entries are non-negative, right? Then that gives you like a regular decomposition, that gives you a regular decomposition of A as a tensor product. So the idea is kind of like, there are more requirements on asking the decomposition to, have non-negative entries. So maybe there are some decompositions which are shorter if you are willing to tolerate negative entries. You get a rank would be lower than a negative rank, or I think non. Now, here is something that is important actually. But what I was saying, and I'll give you an example where they're different, so that you see that they can be different. But in the rank of the matrix one, then they do coincide. Okay. And actually we did prove that. And so this is not a silly question, because like we did prove that with the joint probability distributions, if you remember, that was a problem about that. Well, I'll remind you what the problem said, but here's like a claim. if the rank of the matrix is 1, then the positive rank or the non-negative, if, of course, here I'm assuming already that the matrix A is non-negative, then the positive rank of the matrix will also be 1. Okay. And that is actually, we did kind of like something like that for the problem of the joint probability matrix. When I told you, well, when the rank of a joint probability distribution is 1, you can think of it as a tensor product of two probability vectors, right? But we had to make sure that they were the probability vectors, so we didn't need to guarantee that the entries were non-negative, if you remember that part. So I don't know if let me see if I can write it down. If you remember, like if we had like the joint probability matrix, if we had rank 1, then you could express it as a tensor product, no, of two vectors, right? But what I had told you is like, yeah, from the linear algebra, you don't know whether the entries of these vectors are positive or negative, especially because you can always rescale them, right? You could always rescale them by a factor, right? So there's always some ambiguity. But one of the problems that I had given you was to show that you can always choose a rescaling that make these entries equal to the marginal probabilities of the matrix, right? So we kind of had done this already. Basically, the proof that we did kind of works in almost like exactly the same way as before. So we kind of did this already. For for the for the case of the joint probability distributions. Oh, but actually, these already give you like a useful reason why this graph is interesting. Because what happens here, okay, so why is this a useful concept? Why is a rank, this negative rank interesting? Okay, let's answer that. So here's an example. If you take the joint probability distribution, right? If you take P, if your matrix is P, which is the joint probability distribution, then if say what happens if the non-negative rank is a number R plus, right? If the non-negative rank of this matrix, if the non-negative rank of this matrix is just some number R plus, that means that P, right? The matrix P is a sum of rank 1 tensors, right? If all the entries non-negative, right? And that's the difference now that all the entries will be non-negative. So all of these have non-negative entries. Okay, and okay, let's just take my word for it for a moment. I can do a rescaling of this to re-express this as we haven't talked about convex combinations before. Okay, so what I'll say is that I'll write it down in a moment, but the idea is that if you do a clever rescaling, you know, these you can rewrite as a sum of TIs times PI tensor QI, where the TIs are numbers between 0 and 1 that add up to 1. That's what a convex combination is, where here. So there's some rescaling happening here, which I'll tell you how to do it in a moment. Where the sums of the TIs are between 0 and 1, and they add up to 1. And each of the TIs and QIs and probability vectors, all their entries also add up to 1. And these PIs and QIs are probability vectors. So what is happening here? That this is just some matrix. This is like a joint probability distribution, but of independent random variables, because this is, you know, if you have a tensor product of the probability vector, that's a rank one joint probability distribution. So if you call this a matrix PI, called PI tensor QI, this is a rank one matrix joint probability distribution. So it's kind of like constructed out of independent random variables. So this is doing is you know, like in statistical language, what this is doing is expressing the P as a mixture of independent joint probability distributions. So it's kind of like you're trying to find the independent causes that produce like the total joint distribution. So that is super important, you know, like it's kind of like what is the minimum number of factors of independent factors that produce the joint distribution? And this is what the positive rank does. As a convex combination, like, you know, it's expressing the, you know, the joint distribution as a convex combination of like independent causes, you know. So the idea is that this is kind of like, because it's like graph one, the distribution is kind of like those that matrix is produced by independent factors. So you're expressing the overall global distribution as a sum of like the independent factors. So that is obviously very important. That's a lot of statistics, you know, like I think it's called like mixture models, something like that. You know, they're trying to express a joint distribution as a mixture of like the independent process, you know, they're trying to find out the right process. So that's like a very useful application. And there's also like this application. Here's another interpretation now for the latent semantic analysis. Okay, so this is just for the joint distributions. Okay. Here's another application. So if you go back, oh, sorry, yes.
Yeah, I've got a question. So I assume that I assume because when we scale that we did
Okay, they don't come from FPV. Yeah, no.
but something similar that
No, it's actually you know, when like I was going to write it maybe a bit later, but you know, let me pull up the preamble here. Okay, the idea is that, you know, if you have, oh my god, it's just like this stupid notation. Like how am I calling this stuff? Uh, or how? Well, it's kind of like easier to kind of like think about it from the matrix product perspective. The idea is that there's always a lot of ambiguity. I mean, these factors are definitely not going to be unique. It's not like SVD. I still have, there's more things that I have to say, but this is not going to be like SVD, which is more or less always unique, like after the different conventions. I mean, not that this is super, you know, super terrible. But for example, you can multiply, you can always sandwich like a diagonal matrix that is inverse in between the two of the right side. And you can kind of like use that to play with what the columns are supposed to add up, for example. So that is kind of like closer to this scaling. Yeah, that's closer to the T. I mean, the T is a little bit different because it's for the joint distribution, but it's more like along this line rather than kind of like come from an SVD perspective. Yeah, here like the SVD, like it's not. I mean, obviously, I will comment on how do you find how do you find a non-negative matrix factorization uh for the matrix, right? It's kind of like there's something called non-negative least question. Especially my so there's kind of like an adaptation of these squares, creating the same thing that you do, but you want to include the negative conditions of the answer. But yeah, I mean, it's and now and like obviously I did try to set it up so that it would look similar to what you're doing with SVD, but it does have like very distinct flavor just because SVD do have like more uniqueness behind it, whereas here they're like, you do have to add extra conditions if you want to kind of like reduce the factors that can show up. Like otherwise there's like a lot of them. There's going to be infinitely many options that can go and in like in what the factors can be. No. No, but the trick is not too bad, but you know, like I don't know if I'll mention it today, but yeah, I'll definitely say it like next time. Um, like what I was going to say is like in this bag of words model. Okay, let's think also about the bag of words. Um, so again, if you think of the A representing the term by document matrix that I had before. Let's say you find a factorization for the term by document matrix. What does it mean? Again, you can kind of like think of this in terms of what does it mean for a specific column of A. So, oh my God, let me see what's the best notation here to write. So, let's say A sub J. So let's say that A sub J is the jth column of A. That's not too bad, actually. Okay, so how does this give you? Let's see. So this again, this was an M by N matrix. This would be an M by R plus matrix, and this would be an R plus by N matrix, right? So it would if that if you kind of like if you do the matrix the interpretation for the matrix multiplication that expresses that this equation expresses a particular column of A as a linear combination of the columns of W. We can like go over the details. So that the previous equation means that okay, this is column K, if I'm not mistaken. Yeah. So This is W is here the K column of the matrix W. Okay, so WK here is the kth column of W. So what this is saying is that again, this column represented kind of like a document, right? Like in the standard document matrix. So this is expressing a particular document as a combination, but the thing is that all the entries here are negative and non-negative, right? Like the problem is that when you have, that's why it's useful to have these non-negative factorization, because that if we're working with probability theories and things like that, or frequencies, you can only interpret as a negative frequency. So what does it mean to say that a document is like negative one third, like one of the column of this negative stuff. So you want to have like it's more transparent if you have like if you have all the entries not negative, because then that does give you um, a more clear interpretation. So what this is saying is that the document, so because again, this was the case, the jth document that we were studying. Then this gives you, this expresses the jth document as a combination, as a linear combination of the, well, even more than that, because it's a negative linear combination, right? Because these weights are non-negative numbers. So let me just emphasize that these weights would be non-negative numbers. So this expresses as a non-negative combination of the columns of W. But again, there's a trick that you can do here where you can assume that if you do kind of like a trick like by multiplying by the inverse of the diagonal matrix D, then you can assume that the columns of W are also growth stochastic, meaning that the columns of W also add up to one. So that represents okay. So if you can assume, let me put it like this. You can assume that the columns of W add to one. That each column of W adds to one, each column. Okay, why is that useful? Maybe I should go back to the beginning when I was writing this, my example with the sentences, right? Because here, the way I'm thinking about a document is as a probability distribution over words. So what does it mean to have a document? It means that you are assigning probabilities of occurrences of particular words, right? So if you know that the columns of W add up to one, you can interpret each W as a document itself. Each column of W is a document itself. So it's expressing every document you were working with as a combination of documents. So they are kind of like a basis of documents, and they are called topics because that's what a topic is supposed to be. If you say that, let me find a book on economics, like the idea is that kind of like expresses, like that topic economics expresses like the appearance of many words, finance, money, interest, etc., etc. So the columns of W are interpreted as topics, like document topics, that's usually how they're called, because every other document is a combination of those topics. Uh, so it's a little bit of a word salad, but I'll put some examples so that you can like see it out, like work it out, like so. But the idea is that so if you have that each column of W adds to one, then each column of W is a document itself, can be interpreted as a document. each column of W can be interpreted itself as a document. But it's not like a basis of documents, but when they're called topics. That's kind of like what a topic is supposed to be like, So the columns of W become a basis of documents. So they are regarded as topics. So for example, in my sentences, just to go for a moment, depending on how, when you set it up, like, these sentences, like, refer pets or to food, like, think of the bones of the milk as food. So kind of like the idea is like, in a sense, like the topics could be related to pet, to animals or to food, like, and then kind of like those are kind of like the basic columns, and then like everything is expressed by combination of those. So like the idea is like, you know, it's useful because that way you can kind of like see how much of each topic contributes to generating the data. That makes sense, kind of like so far. So it's a useful concept. Hopefully, it kind of like looks more plausible that it is worth something, because again, like having non-negativity can, uh, you know, they're kind of like the shtick is that if you care about compression, but you also care about interpretability, right? So the rank is useful to compress things, right? Like we talked about this, like once you have the rank, you can even like approximate it by truncating the rank and all this stuff. So rank, having low rank or things like that is useful for compressing, but that may lose interpretability. For example, like the data you had with like always has to satisfy certain requirements like negative. That gets all messed up when you're doing an SVD compositions and things like that, because you can easily, start with a matrix which was all with non-negative entries, and then you do SVD and you truncate the rank, and you'll have like negative and positive end. So that doesn't have like the same interpretability, because if you were thinking about everything in terms of probability distributions, and you're stuck, like, well, again, what does it mean to have like a negative probability and things like that? That's right. So by trying to preserve the non-negativity as much as possible, which when we make it factorization by four, then you get like this interpretability makes more sense when you are actually. Maybe just to I'll say more about this next time, but just to kind of like just to mention some properties of the negative rank, some of which they're easy to verify. But let me just write them down. And maybe I'll put them as a problem if someone wants to work them out. They're not too bad. They're not too hard to convince yourself that they should be true. No, but it's actually like a very interesting question. When does the rank equals the non-negative rank? Determining the non-negative rank, I think it was like NP hard as well. It's like kind of like a more complicated problem than determining just a rank. So again, A is an M by N matrix. So the idea is that, as I was saying, that the rank of A is always less or equal to the non-negative rank. So I'll call this rank plus of A. And this is also useful to know, because even from what I have said, like, you could have said, oh, this explodes to infinity, you know, like, how do you even know that this is not like a infinite number, you know, like, that it could be divergent, you know? Well, no, it's always bounded by the number of columns on the row, it's kind of like this, kind of like the same argument that, you would do as before, so this will not exceed the, you know, it cannot exceed the number of rows or columns. And in fact, the non-negative, another property is that the non-negative rank equal the non-negative rank of the transport, which is supposed to be like that. Yes, that's also good. Okay. Yeah, sorry.
How do you go about, like, how do you know you're preserving as much value in the enrichment, which is a consumer factor?
Well, it depends, what you mean by preserving,
Like, I mean, like, because like, obviously, like, you have to change some values that originally, to develop the original ranking of the
well, let's see, like, yeah, let's,
It would always
no, like, so,
survive.
right, like, so,
Oh.
it depends, right. Is that, you know, there are two things at play when we were talking about rank, which was like the actual rank versus the truncated rank, you know, when you do like a truncation, right? So this is literally an equality and it's thought of as a perfect, like that, the A is literally the sum of this rank, R rank one tensors, right? In practice, you want to find a low rank approximation, in which case you would truncate, right? And then you don't keep the full, like the correct rank.
You can like add up the base.
Correct, like you would like maybe take that, well, which obviously with the SVD decomposition is clear what you should do because you just keep like the largest singular values, however you wanted to consider. So it's something similar here where like, when I write it this way, I literally mean it as an actual equality, as in these will act entry by entry coincide if you were to kind of like do the expansion. In practice, of course, you do want to find low non-negative rank approximations for the same reason in which you want to find like low rank approximations to them. And there, like, you do have to, truncate, but the truncation is kind of like harder. I mean, it's less obvious because there's no analog of singular values in this context. So the way I will explain it next time is more kind of like a least squares, kind of how we were doing like recently, like this gradient descent, where we will go more along those lines. That kind of like does survive better in this case because there's not like a canonical decomposition similar to SVD. So that's why also I was talking about gradient descent and all this stuff like before, because there you kind of like do like a least squares, but alternating, but you have to add like this extra condition that the entries have to be non-negative. That's kind of what adds an extra fun flavor to the problem. Uh, but yeah, as a but here it is thought of as an actual equality. But then yeah, you do want to get into the truncating business, which you definitely for practice will be interested in doing. So right. So yeah, like eventually you will find a low non-negative rank approximation to these things, and that's totally fine. But if I write it as of how I was writing it, I did mean like a perfect equality, so there's no error, there's no, yeah.
Yeah, that makes.
Okay. Yeah. I think yeah. No, I think it's like a good place to stop. Let's stop here, and then next time what I'll tell you is more like, yeah, how do you find, how do you find the approximation and other useful properties about this? But I just wanted to introduce this because, like, again, I wanted to have like a flavor of all the useful definitions of rank. So there's a normal rank that there's a symmetric rank. For tensors, there's something called the symmetric rank of a tensor. For symmetric tensors, and this is kind of nice. So symmetric tensors are kind of like the analog of symmetric matrices, and that it's also useful to know about those. But I thought, okay, let's just do this first because it's a very difficult concept. So I'm doing the linear algebra part first, and then you take a tensor train decomposition. You know, you apply kind of like non-negative factorization. You know, kind of like you can kind of like extend these to tensors. But we'll go slowly. So next time I'll tell you more about how do you set up everything with least squares and all this stuff like. But yeah, listen here because I'm almost done out of time.